Okay, good afternoon, everyone, and welcome to this Spotlight talk of EFCE. I'm Giorgio Veronesi. I'm the president of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for 9 years, and currently I'm in my second term as a president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects, mainly abroad, with several assignments overseas. I'm very happy to be involved in the introduction of this webinar on high gravity technologies for intensified reaction and separation processes, which combines process intensification as well as chemical reaction engineering concepts. And I'm looking forward to participating to it. Let me say something first about the Spotlight Talks. It's now our 6th year of this initiative, which started in 2020 to keep together the chemical engineering community during the COVID pandemic. But the success of the initiative convinced the board of EFCE to transform the Spotlight Talks in a regular feature of the EFCE program. So now we have one Spotlight Talk series in odd years, like this year, and two in even years. This spring, 11 of our working parties and sections, which are chemical engineering applied to medicine, sustainability, chemical reaction engineering, this one, process intensification, this one, comminution classification, mechanics of particulate solids, fluid separation, polymer reaction engineering, static electricity, crystallization, early career chemical engineers are delivering over 2 weeks 10 webinars with talks on specific topics by leading industrial and academic experts. You can find the whole program on the EFCE website. EFCE promotes scientific collaborations, as you know, and supports the work of chemical engineers in all European countries, representing more than 100,000 of chemical engineers. And the EFCE working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE activities. So they provide an important forum for technical exchange and networking among chemical engineers in Europe and also outside Europe. So before concluding, I would like to thank all the people who work hard inside the working parties and sections and EFCE in general for this initiative to happen and to be successful. In particular, I would like to express my thanks to Martin Pou in Toulouse, who did most of the conceptual setting up and practical activities. And I'm very pleased to inform you that the EFCE board has decided to award to Martin the prestigious Dieter Behrens medals for a contribution to chemical engineering that will be delivered at our European conference in Lisbon in September. So thanks, Martin, and congratulations for this well-deserved award. So I thank you for your attention. I wish all the speakers and the attendees a fruitful and successful webinar. I would like then to give back the word to the chairs of the two working parties, and I will start with Professor Georgios Stefanidis, the chair of the Working Party on Process Intensification. So, George, please go ahead.
Yes,
Thanks.
thank you, Giorgio. Thank you, Mr. Chairman. I'm Georgios Stefanidis. I'm the chairman of the EFCE Working Party on Process Intensification, which currently comprises 27 members from industry and academia across Europe. First off, I would like to welcome you all, the speakers and the audience to this webinar. And of course, particular thanks go to EFCE and to Martin Pou in particular for taking on the organization and dissemination activities related to this webinar. And of course, congratulations on this award that Giorgio just mentioned from my side as well, Martin. The webinar of today is the third joint effort between the two working parties on CRE and chemical and process intensification over a period of less than 2 years. which basically shows the common interests and common ground of the two working parties. Kevin probably will say a few words about the shared working party. I'll say a few things about process intensification. PI, as most of you may know, involves development of novel equipment, processing techniques, and operational methods that in principle have the potential to bring about significant improvements in process plants, in terms of resource efficiency, overall process economics, and reduction in volumetric footprint and environmental impact. The mission of our working party is to disseminate knowledge on PI and promote PI in education, research, and chemical industry across Europe. So in this frame, the webinar of today is on Higee technologies, high gravity technologies that can enable separation and reactive processes in multifold gravity centrifugal fields and bring about highly intensified mass energy transport rates with all the positive concomitant effects on process efficiency and process economics that this intensification entails. So the overall time length of this webinar will be approximately 2 hours. We have 4 very knowledgeable speakers, 3 of them from academia and 1 from industry, who will address different types of Higee technologies and different applications, although the emphasis will be on rotating packed beds. There's a 30-minute slot reserved for each talk. We have asked the speakers to conclude their presentation between 25 and 27 minutes, so there's 3 to 5 minutes left for questions. I'd like to ask you, the audience, to type in your questions in the chat box or in the Q&A box, even better. And at the end of each presentation, we're going to collect the questions and ask them to the presenters. That's all from my side. With that, I'd like to give the word to my colleague, Kevin van Heem.
Thank you, Georgios. So also welcome from my side. So I'm Kevin van Heem. I'm a full professor at Gent University and also director of the board of Laboratory for Chemical Technology. I also would like to congratulate Martine because she's a very important person within the EFCE community. And as Giorgio already mentioned, that without this huge effort, indeed, a lot of very nice activities within the EFCE would not be arranged. So well deserved, and yeah, big thanks for all your work during the past decade. So I'm also director for the working party of reaction engineering, and is of course a crucial field within chemical engineering that focuses on the design, analysis, and optimization of chemical reactors. So it's about understanding and manipulating chemical transformations on a commercial scale to produce desired products safely, economically, and efficiently. And you will see that also in the talks that have been selected. And you see also this very strong interaction with the field of process intensification. So of course, process intensification, I will summarize, is doing more with less. And in this case, we put it really to the extreme, Higee. So we have some very nice talks today. Because of the critical aspect of time, I think we need to be handing over the word to our speakers. And I would like to introduce one of our first speakers, is Professor Yong. He's affiliated with the College of Chemical Engineering at Beijing University of Chemical Technology. And his research interests include high gravity technology, chemical process strengthening, heterogeneous catalysis, and preparation of nanomaterials. So with this, Professor, I would like to give you the word for around 25 minutes. The floor is yours.
Okay, thank you so much. And so then now I can share my screen. So have you seen my screen?
But it's not a presenter mode yet, so we see all your slides now. Yep. Okay, perfect. Floor is yours.
Okay, thank you so much, and thank you for the president of EFCE and also the chairman of the process intensification and also the chairman of the chemical reaction engineering for the invitation. And I'm so glad that have this opportunity to give a brief introduction of this Higee technology and in BUCT. I hope that everyone can see my screen and also the voice is okay for you. If you find that the voice is not so good, just let me know. Okay, so I will start my presentation, and I am Yong from Beijing University of Chemical Technology. We call it BUCT, and my presentation is I call it the process intensification for sustainable chemical industry based on high gravity technology. And today I'd like to first I just take 1 or 2 minutes to give a very brief introduction of BUCT, and we are founded in 1958, and that time. So this time we are in China. We call it the 211 the program. It means that the BUCT is one of the top 100 university in the whole China, because in China we have more than 5,000 universities, and we have 3 campuses, and the oldest is this East campus here, and this is the photo of our campus in BUCT. Okay, and we have like just 2,300 the faculties to do this research, and we have like 26,000 students, and including the undergraduate and the master and the PhD, and also we have like 500 international students. We BUCT, we just that's our university name. We're including the chemical technology. So we focus on this chemical engineering, material science, mechanical engineering, and also the information sciences. So today I give the very brief introduction, including the 3 content. First, I'd like to give a very brief introduction of this Higee, the history. You know that here we are just, I think here this is very conventional, the pocket column. And we know that if we are use this column for the distillation, and the gas will be introduced as the bottom, and then liquid will be introduced as the top. So this gas we will have like the pressure for the driving forces, but liquid, when you're at the top, flow from top to the bottom, and then the driving force is only the gravity force. So we call it gravity environment on the areas, but the mass transfer rate is sometimes slow. In 1979, and ICI company, they have give a very smaller column, and then they put it in the NASA and in the aircraft in Spain. So the gravity force is the microgravity environment. So you don't have the driving force for the liquid. So liquid cannot flow from the bottom, from the top to the bottom. So it means that the gas and liquid, they don't contact each other. It means that they don't can finish the mass transfers. So the mass transfer rate sometimes is equals 0. Then people are thinking about it. If you can just speed up the liquid flow rate or the flow velocities, it means we increase the driving force for the liquid. Maybe we can just speed up or increase the mass transfer rate. That is the original idea for the Higee introduction. So on the areas, how we can get this high gravity environment? So people are thinking about it. If you can just rotating this pocket column for 19 degrees, then we fix this column on a rotating disk. It means that we can rotating the columns. So the liquid, they will have like the increase. Another forces for that is the centrifugal force. It means we can use this centrifugal force to instead of these gravity forces. And we called it, this device is called, we rotating the particle bed, so shortened as the RPB. Then people, in the past time, people found it that if you have this RPB, these devices, and then we can enhance the mass transfer by 1 or 2 orders. So we call it this new technology as the Higee. It means high gravity. High gravity is the technology name, but we called it these devices, we call it RPB. So how about this RPB? What it can be used for? And for us, just when we are just go to the textbook, we found it that if you are design a column, and maybe we can see that it means they have 2 very key parameters. The first one is that we need to just design we need to identify the diameters. Sometimes it means that for the diameters is commonly we are determined by the capacity. It means how many gas flow rates for you need to design the diameter. But the heat, it means just in the textbook, the heat, they are equals to this NTU and HTU. So NTU is the number of theoretical units, and HTU means the heat of the theoretical units. And the NTU sometimes is divided, it's determined by processes. If you use this column for the CO2 captures, and if you give the targets, we need to have 99% of the CO2 capture efficiency, and then they are determined at this HTU. HTU means they are related to the devices, and they are related to this mass transfer coefficient. We call it KYA. So it means for these equations, if you can increase the KYA by 10 times, then you will decrease this HTU by 10 times. It means here, if in this RPB, if you can just increase the KYA, the mass transfer coefficient by 10 times, then you will decrease the heat, the HTU by 10 times. So the H will be by 10 times. It means here you need 10 meters height, but here RPB only 1 meters. So it means we can reduce the size of these devices for that. Another thing is that if we can just increase by 100 times, maybe you can decrease here is the 100 meters, here is the 1 meter for that. So this idea is just the way to do the calculation, the principle of this RPB. Why this RPB technology, this Higee technology, they can decrease the size of the devices. So this is the typical the RPB, the diagram of that. This is just like the gas liquid systems. We can introduce the gas as the shear, and then the gas we can flow across the pockets, then they can go flow out of the RPB from here. The liquid we can introduce at the center of these pockets. So when the liquid introduced in these pockets, then they can be cut by this the pockets, and then the pocket will cut this liquid to be the liquid film, liquid droplet. So you can increase the liquid surface areas to enhance this mass transfer for the gas liquid system. Also, this micro mixtures of the liquid systems. And there was an example for just divided by BUCT, and this is where use this RPB for the CO2 capture for EOR. This is the original pocket column. This is RPB. So we can see the size is almost 1/10. It means that the equation we just analyzed it before. If you can enhance the mass transfer by 10 times, then you can decrease the H by 10 times. It means here is the 13 meters, and here is the 3 meters for that. And basically, we are commercial use of this RPB in these gas liquid systems, liquid systems, and also the gas liquid systems. And I will give some examples later. And I will just spend a little time and very fast to go through this fundamental of this Higee technology. And you know, any technology when you need to from the lab to the industry, and we just give very just that's the we see the some data from that one new technology from the lab to the industry at least almost just like 10 years, 8 years like that. So this Higee technology in BUCT also the same, and we take really very long time, almost 10 years to this fundamental research and like the hydrodynamic micro-mixture mass transfer reactions. And the BUCT we are published more than 600 papers, and we are holding 115 patents for that. And like we use these high-speed cameras, and then we can look inside the parkings, how this liquid they can break up to be the like the liquid film, liquid ligament, or droplets. And also we can just do some calculation of this, what's the size of this droplet. And then also we do some study of these distributions of this liquid droplet. And because this RBB and they have a rotating the characteristics. So sometimes we use the conventional technology, we cannot get inside. How about the liquid inside inlet? So we use the CT X-ray to look inside how this liquid can be distributions. And we can use the CT ray to look inside it and get the data or the information of the liquid distribution, also the liquid holdup of that. And another thing is that we use this CFD to just simulate the liquid and gas flow inside the RPB and can get some like the pressure. Also, we can find some special phenomena. And for the mass transfer models, we are divided by the viscosities to be like the 3 models. And the low viscosity, we are use the droplet models. And the medium velocity, we are use the surface renewable models. And the high viscosity, we use the film models for that. And with the liquid velocity, is just like the CO2 captures, and we use the droplet models, and the deviation is about 10%. And they use the middle of the liquid viscosities, and you see that the deviations, the errors maybe is a little bigger. And if you have this high viscosity and the models, and the errors were also bigger than that. Just I'd like to say for this viscosity, just the fluid, the liquids. So sometimes the physical and the chemical, the information, the properties, the parameters, sometimes we can get the very correct the data for that. Sometimes we use some correlations to calculating this, just the velocity, density, a lot of things. Even when you treated this high viscosity velocity, sometimes they will change a lot by this, like the rotating motions, because you have the shear force on it. So sometimes the viscosity is the change a lot, and also the density. Any physical parameters will also change, so that's leading the higher errors for that. And also we are building that like this micro-mixture and reaction models to building the reactor models for that. And so the fundamental research, I think is sometimes we are the most important is that we use this for this scale up, because if you want to go to the industry, that should be to be like to get the know-how how to scale up this RPB and how to just to design an RPB reactors or separators to fit the processes of this industry meet the requirements. So then I'd like to just share some industry applications of Higee technology, some cases like the separation reaction and also some nanoparticles. And first, the application of separation processes. And we know that for this RBB technology or this Higee technology, the first the application is that just we have this paper in 1983, a pilot test to use this RBB for the continuous destinations. But here, they use the true RBB to just to finish this the continuous destination, because one RBB waits for the stripping and one for the destinations. And the because if you have true RBB to replace one columns, and people were thinking about it because you have a lot of just the connection pipe valve, and also you need to very careful for this control. So BUCT in 2006, we thinking about it, we used the one RBB with multiple rotors for this continuous destinations. Also, I know that's the another university in China, we call it Zhejiang University of Technology. They invented the RZB also for these destinations. For just both of us, we use the one RBB to finish, just to replace the one column, destination column to finish that. So if you can use one shear with multiple rotors and the collides, they will accept this technology very comfortable, because you also one devices, another one the conventional technology, also the one devices. And also we see here, I don't know, this is a conference paper or just academic papers in 1997, and just people write it that we have the vision in 1997 from the UK. People think about maybe in 2010s that we can put all the big columns inside houses to do that. So I think yes, the BUCT, I think we see these technologies, we really put this RBB and inside the houses, so the dreams comes true. And here, this is the conventional columns, and we replace these columns and use a very small RBB. And the orange column, the height is almost more than 21 meters, but our RBB is like the 3.6 meters height for that. To use it, we use this for the methanol water separation by these continuous destinations, and the capacity is like the 50 tons per day for that. And another case is that we also use this RBB, and you see here, we put just between two floors inside houses to do that. And we also just say a lot of this skid, we call it RBB destination skid for the client, because if you have the small RBB, then you can put and fabrication, everything in the fabrication shop to be a skid, then just the transportation to the skid to the factory to finish the installation. So when we can solve a lot of monies on the transportation, fabrication, installation, and a lot of things. We can imagine that if you are building a column just on site on this chemical plant, and because the column, they are very little big, and the height is very higher, so you need to fabrication it on site sometimes to save the transportation fee. But for this RBB, it's very easy for us. We only just the fabrication everything and can do the commissioning everything just in the fabrication shop. Then we sell, we shift to our client to do that. Even for this RBB, sometimes because it's very smaller, and then the liquid hold up will be smaller, so we can decrease the safety issues because liquid hold up decrease a lot. Another is that because this RBB very smaller, it means just for this RBB, if you are operation or open or you are turn on or turn off the systems is much more easier for you, because they are just 5 minutes you can get the stable, the operation running for that. Okay. So another one is just we do some offshore cases. And the first case is just you see the pictures we are taking in 1998, November. We have RBB for on the offshore to remove the oxygen from the sea waters. And then we put this water injection on the ground offshore, then to get the oil out for the EOR. So the capacity is 215 tons per hour. And I think this RPB also is like, I think it's very big RPB at that time. Okay. And at the later time, we also have do some projects with the 500 cubic meter per hour. It means have 500 tons per hour for the seawater. Also remove the oxygen from the seawaters, and we use this is for the FPSO, and with this RPB also just gets removed oxygen from this water, and then for the EOR for that. And another case is that we use RPB and offshore to remove the H2S from this natural gas. And in China, in the past time, and people were burning the coal to get on in the north of China. But in order to protect the environment and protect the air, and the government just asked all the people to burn the natural gas to get on. So it means just in China, all these just the state-owner companies, they should to recover all the natural gas, because we don't have so much natural gas. We even buy this natural gas from from Qatar and also from Russia, America, and Australia to get the natural gas. So here, this is a platform. This platform originally they are designed for to dig the oil, to get the oil out. But when you get the oil out, there are some natural gas will be also out. So sometimes in the past time, the people were burning this natural gas and then burn it. They don't recover it. But right now, government asks all the people to recover this natural gas. So you need to do that. But if you need to just recover this natural gas, you should do that. You should to remove H2S, remove CO2, remove water, and do a lot of purifications. Then you can get this natural gas. So these projects we are cooperation with the CNOOC and CNOOC. That's the gas company in China. And the original the proposal is that the American company, they give the proposal to give a very big column to remove this H2S from this natural gas. But if you need to just the installation a big the column, and you should just to across like maybe 6 the floor of this the platform. You need to do a lot of work to do that. But BUCT will propose like an RPB, just a very small RPB. Then we don't need to just dig a hole on this tank. We only just put it between 2 tanks to finish the processes. So it means that we can just reduce a lot of spaces and areas, and also we can reduce a lot of investment. We do the rough calculation. When we use this RPB, CNOOC, they do the rough calculation that if you use RPB, we can save like 0.1 billion RMB for these projects, because this is offshore. The cases, everything is very expensive. And also we use RPB and for this water removal from the natural gas, and this is in the China Baltic Sea, and we use the TG to remove the water in these platforms. And 1 month ago, and I go to this platform because this RPB we used for 8 years, and the client, the customer, they wanted to do some maintenance for that. So I go to this platform, and you see here, this is some rooms can be used for people to live. And here, this is the helicopter, the platforms, and our RPB is installation here. Okay. So this is here.
Okay. Just say 3 more minutes if it's possible.
Okay, how many minutes left?
3.
3 million. Okay.
Yeah.
Yeah. Okay. Some gas like the refineries, and we also have lots of cases and to remove the attitude from this dry gas, and also from this cloth gas, and with this tail gas in refineries, we also remove SO2 from this tail gas, and also remove the SO2 from the flue gas of that. And for the reaction cases, I can give you some examples. The first one is the MDI reactions. We use RBB to do liquid reaction with the condensation reactions for these processes. And we put this RBB in the, they have 1 million of the MDI, the products. This is the product of the RBB, the technology for that. And another one is that for LPG sweetening technology, and we use the RBB for these processes, and also we put it for this commercial use of that. And this is also the technology we are just do some comparison with RBB with this European Melox technology. We use one RBB, but the Melox used the one column and one tank, and we think the volume is the one is reduced a lot. Okay, we get some promotions use the line intensive scale RBB used in this refinery process. Okay, some nanoparticles, I think this one is maybe people don't care about it, and also we use this RBB to produce these nanoparticles by these Higee technologies. And we also do some like the zeolites and the VPO catalysis and hydrogenation catalysis for that. Okay. So the last information is that for the CCUS. And we do a lot of things to this CCUS. We use RBB to replace this column. And we have the lab scale and the pilot scale and the demo scale and also the commercial use of these RBBs. And till now, our BUCT, we are like the 200 industry application cases for this for all different kinds of processes. And we really think that this Higee technology is a platform PI. The red upwards means we do this commercial use for that. And we thank a lot of our partners in China and out of China. And okay, thank you so much. And just a very quick presentation of this Higee technology.
Thank you. Thank you for a very nice presentation. We have a question in the Q&A part. What is the comparison of operating costs for a rotating packed batch compared to conventional column? For example, if you look at for example, if you compare for CO2 or for the H2S applications, so what is the difference in cost? So CapEx.
Okay, thank you for the chairman and for your question. And for the operation costs, I think just like we can give the example of the CO2 captures. And if you are just because here for this RBB, you can shorten the size, the volume of these devices. It means that you can reduce the liquid holdup inside. It means just like you use MEA, and then MEA the MEA you bought it, you can reduce a lot of that. This is the fixed investment, not the operation costs. And another one is that because for these CO2 captures, we including the adsorption and the desorptions, but almost like 13% of the energy consumption is just for these desorptions. And for the desorption, you need a lot of the vapors to heating everything. So it means if you can enhance the mass strength and the heat transfers, you can save a lot of these vapors. So for our cases, for this RBB, for the CO2 captures, we can reduce the energy consumption by 15% of that. Thank you so much.
Okay, so you mean 50% you can reduce the energy consumption for the CO2 capture? 15?
Yes, 15%.
Okay. And this was independent of the solvent that you use, because I assume that's if you use MEA or other solvents like piperazine or something, that the numbers might change.
For BUCT, just when we use this RBB for this CO2 captures, when we do some like the pilot test or even in the lab test, I think different kinds of the solvents we will test. But sometimes if you have a client, they already have this solvent. It means we cannot change the solvent for them.
Yep.
So sometimes if this is existing systems, people already have the solvent, and the BUCT will ask people to provide some solvent for us, and then we will test the solvent in BUCT by the RBB to test it. But if there are some just new building things, we will propose BUCT solvent to the client, and also they just fit the RBB very well, so we can sell all the whole process package to the client.
Okay. One last question. What about maintenance? Is it more maintenance intensive than conventional technologies or not?
Yeah, for the maintenance, I think this is a very good question. Just I share with you 1 month ago, I went to the platform in the China Sea, and because that RBB is used for the water removal by the TEG, and that RBB they are running for 8 years. So sometimes that is the cases and 8 years, but this RBB also they can run, but according to the whole things, people thinking about it, 8 years, they should be how to do the maintenance. So we get everything, we get the cover out and get the parking out, and also the bearing everything out, and to check it. And maybe we need to just change something for that. And another issue is that for the maintenance, just like refinery in China, and every refinery they will just at least 4 years for the maintenance for that. It means this RBB, if you want to use in the refineries, you should make sure your RBB can run it for 4 years with non-stop for that. And we have lots of cases for that. So for the maintenance, sometimes we suggested for this, just like maybe the gas liquid systems, we suggested that 4 years you can do the maintenance for that. So maybe for any other cases, just like maybe solid something like that, that's some very special one. We suggested maybe 1 year for the maintenance for that. Okay.
Okay. So thank you very much. I really appreciate your talk, and I probably will send you a mail to share your slides because they were very clear, and also a very impressive number of patents that you have. Okay, so thank you. And this means we can move to our second speaker of the day. So
okay, thank you so much.
Thank you. That's Professor Jonathan Lee. He's a senior lecturer in chemical engineering at Newcastle University. He focuses his research on innovative process intensification techniques, and a key area of his expertise is utilization of rotating backplates for enhanced mass transfer. So, Professor Lee, then I would like to give you the floor. Let's see if you can share those slides. Yeah, because that's always a challenge in this kind of environments.
Okay, here we go.
Yeah, perfect. Okay.
Okay.
Floor is yours.
Okay. Okay, thank you. So I'm going to talk about my work, which is involved in using intensification for CO2 capture. I'm a professor of carbon capture at Newcastle University because I work also, besides working in this area, I work quite a lot in algal-based carbon capture as well. So just the talk outline, I'm going to briefly describe solvent-based CO2 capture, how we intensify it, and certainly from a European perspective, what's going on at the moment in that area. Talk about scaling up the RPB absorber and a little bit about the solvent regenerator. So this is a solvent-based carbon capture process. Basically, the flue gas comes in from whichever source. There is some gas treatment that goes on. So that might be sulfur oxide removal, nitrous oxide removal, and some cooling. It then goes into the main absorber, where it's contacted with a solvent, most often an amine, and that removes the CO2 by reacting with it. And the gas then passes into a water wash before leaving the plant. The solvent goes through an intercooler into the regeneration column, where the CO2 is liberated from the solvent, and then the solvent gets recycled back to the absorber, and the CO2 gets dried and then compressed to go wherever it's going, either storage or use. These are all packed towers. So the flue gas pretreatment, the absorber, the water wash, and the desorber are all packed towers. And therefore, if you want to intensify solvent-based CO2 capture process, you're looking at using rotating packed beds to replace all those packed towers. So for the last 11 years, I've been working with a company called Carbon Clean Solutions, based in the UK, but now quite international. And they have now got commercial processes. They call it Cyclone CC. This is the 10 ton per day unit in the picture there. And basically, that 10 ton per day Cyclone CC intensifies the absorber and regeneration columns. The gas pre-treatment and water wash are done in conventional columns on this particular process, and you can see those in the background of this plant. But that is commercial. Carbon Clean have sold commercial units besides building this 10 ton per day test unit. Now they're moving on, and they're developing this Cyclone CC technology, but where they intensify or use rotating packed beds to replace all the packed columns in a carbon capture process. And so actually, just today, they've made an announcement about this process and the successful testing of some of the RPBs for that. And if you click on the link, you'll get there. Now, there are some other players in this market. So Baker Hughes have got a development of rotating packed bed technology from Norway. And they've actually intensified or used rotating packed beds for the absorber and water wash. And they've also got a design for solvent regeneration, which integrates the reboiler into the regeneration column. And I'll talk a little bit more about what we're doing in that area later on. This is a cross-flow RPB, so it's not counter-current flow where the gas and the liquid are flowing opposite directions. The liquid still flows in the same direction as it does in the conventional rotating packed bed, but the gas flows across the packing, which allows them to basically build the absorber and the water wash into a single unit. And then finally, talk about a project that I'm currently involved in. So this is a European project called Higee Accord, and we're basically intensifying the absorber and we've got the solvent regeneration column, which we're intensifying, and we're integrating the reboiler into that intensification. There's a picture of it on the right. It's being built down in Yorkshire in the UK. And if you click on the LinkedIn symbol, you'll be able to see a time lapse of it being built. So how have we got to this stage? So starting 11 years ago, or a little bit earlier actually, for another project, we built a lab scale unit, which is shown here on the left. And you can see the rotating packed bed in there. You can just see the packing inside it. So the gas is coming into that plastic casing, and the liquid's going in the middle. And we used that 300 millimeter diameter unit to measure the rate of absorption for CO2 capture, the flooding limits and gas pressure drop. We also have a 1,000 millimeter hydraulic test rig next door, and we use this for doing flooding and gas pressure drop measurements. So we use that data to basically scale up from the lab scale here to 1 ton per day scale. Now, the packing we were using originally was these expanded metal mesh sheets on the left, which was basically an adaptation of some material that was used for supporting plaster on walls. And it made quite a good rotating pack bed. But then we participated in the European project, and Mons developed this rotating pack bed packing that's shown on the right-hand side here. And it had a higher surface area and a lower voidage and a lower pressure drop and generally better performance. So those are the two packings that we had when we scaled up for the first time. When we came to scale up, the inner radius that we scaled up to was based on a entrainment correlation published by Agarwal. And that didn't work, and we actually saw some entrainment. So that method didn't prove to be reliable. The minimum rotating speed was based on establishing what we call spray and film flow in the rotating pack bed, and this simple sort of speed limit that we used there worked in terms of establishing the right regime. The axial length was based on a very old flooding correlation for rotating pack beds, but we verified that in our experiments in Newcastle, and that worked very well. The outer radius was based on the mass transfer correlation that we measured for absorbing CO2 at the lab scale, and that didn't work, and I'll explain why. And the gas pressure drop was based on measurements that we made in the 1,000 millimeter diameter rotating pack bed. We actually measured the pressure drop inside the rotating pack bed, and that worked very well. And we've used that to scale up to much larger scales than 1 ton per day. So we scaled up in a project funded by the UK government, and this is the absorber shown on the blue platform. So it was 95 millimeters internal diameter, 1,100 millimeters outer diameter, and 45 millimeters axial height. And we used the expanded metal packing. And we did some tests with 30% MEA, and we got 59 to 66% capture, which is not what we wanted. We wanted 90% capture from this device, and it didn't work. So why did that scale up for the outer radius not work? So I'm going to make reference to sort of work coming out of Beijing here, because they have done a lot of measurements. And so there are 3 mass transfer zones within an RPB. The entrance or end zone, where the liquid comes in, the bulk zone, which is the rest of the rotating pack bed, and the cavity zone, which is where the liquid leaves the rotating pack bed and flows across to the outer wall of the casing. And measurements indicate that the mass transfer rate in the entrance zone is at least 4 times higher than the mass transfer rate in the rest of the rotating pack bed. So we've got this very intense zone of mass transfer right at the entrance. In the cavity zone, the mass transfer rate may be slightly higher, but it's generally around about the same rate as the bulk zone. And the reason for that very intense mass transfer in the entrance zone is because the liquid jet is impacting onto the rotating packing, and basically that jet is being fragmented as it collides with that rotating pack bed. And that's what gives us the very high rates of mass transfer in that entrance zone. And this is very approximate calculation. We think that in our 300 millimeter diameter lab scale absorber, the volume of the entrance zone is about 8 to 15% of that rotating pack bed. So that entrance zone is having a significant effect on the measurements we take from that small scale rotating pat bed. The other thing that's going on in this CO2 capture process is basically the reaction between the CO2 and the amine. So there are two sets of reactions. One is where the CO2 is getting transferred to the solution, which is the mass transfer process, which is very fast. And then we have the amine reacting with the CO2 in solution to give us a carbamate and water, and that's a very fast reaction. And the amine is also helping to catalyze the mineralization of the CO2 by making the environment an alkaline environment. And those are still very fast reactions, but slower than the carbamate reaction. And when we did our work to develop our correlation for the rate of CO2 absorption, we were working with amines at low loading. And so we were seeing basically carbamate formation dominant. And so the rate of reaction was much faster. So basically, if you look at the overall mass transfer coefficient, it has a gas film element and it has a liquid film element. And the expression for the liquid film here reflects the enhancement that's caused by having a reaction going on in the liquid phase. So Kg is a film mass transfer coefficient, and Kap is the apparent reaction rate. So in our 300 millimeter absorber, the mass transfer coefficient, the average value of it was higher than we would be seeing in the 1100 millimeter absorber, and the reaction rate is also higher. So those two things taken together mean that the data we use to scale up to the 1 ton per day CO2 absorber basically underestimated that outer diameter because we were overestimating the overall rate of mass transfer. Now, we were doing this project to scale up to 1 ton per day was a commercial project. And so, it's being driven by a company and they don't want to accept 60% capture. And so we had to think of something, we had to change something to try and get to 90% capture. So we used some work that was published from Germany in 2020, and they were looking at the liquid distribution in a rotating pat bed. And on the left, this image shown here is showing the liquid in red, or its volume fraction as a function of radius. And this is for a packing whose porosity is constant. So the size of the pores there is the same size. And you can see that we get good liquid distribution, but the volume fraction of liquid decreases very rapidly with radius. So if you then do that measurement again, but now use packing that has variable porosity. So here the pore size is going from 2.3 millimeters down to 0.9 millimeters. Then as you decrease the pore size, you hold up more liquid in the packing. And so that gives you more residence time because you're slowing the liquid down. And so working with Monts, we basically developed that variable porosity packing. And you can see the picture of the rotating pat bed on the left, on the right here. Here's some data taken from the 1 ton per day scale absorber. So the orange line is when we are using the Expomet, and the blue line is when we are using the Monts variable porosity packing. And you can see here that the Monts packing has given us a greater percentage of capture, and that's because we've increased the residence time. Now, we still didn't get to 90%. This is with 30% MEA solution. Now, we were doing this project with Carbon Clean, and they have a solvent called CDR Max, which is kinetically faster than MEA. And so when we used their solvent with this rotating pat bed, we were able to achieve 90% capture, which is what Carbon Clean wanted. But that just sort of shows some of the pitfalls in scaling up the rotating pat bed. Now, we've used those lessons in the Higee core project, and this picture shows the 2 rotating packed beds that we're using to capture 10 tons per day CO2. And we've got 2 in series with intercooling between them of the solvent. And these rotating packed beds are 380 millimeters ID, 1,990 millimeters OD, and 185 millimeters axial length. And well, they're being built into a process which will be ready to be tested in Greece by about August this year. Now, you can also intensify the solvent regenerator. And if you're using a rotating packed bed, you can reduce the packing volume by a factor of at least 30. And so that drives the question, that sort of poses the question, well, if you've shrunk the RPB, rather than having a separate heater outside to generate to put the energy into the system, why not directly heat the RPB rather than having a conventional reboiler sitting out there? And so that's what we've set about doing. So here is a sort of schematic of what we call the integrated stripper and reboiler. You've got a rotating packed bed that is completely encased in metal. So it's sitting inside a sort of metal shell, and then that metal shell is sitting inside a pressure vessel, and the metal shell is heated directly by steam. The rich solvent comes in, gets sprayed onto the rotating packed bed, and it flows radially outwards, and then overflows into a scoop chamber where we scoop that liquid out and bring it back to the center and send it out of the machine. And so in the rotating packed bed, it's countercurrent contact with vapor, which is generated by the steam heating. The steam's not directly injected in here. It's heating the liquid in the rotating packed bed and generating the vapor. So that vapor helps to supply the energy for regeneration and strips out the CO2 and passes out of the machine. So we get size and capital cost reduction due to intensified mass transfer, intensified heat transfer, and integration of the regeneration in the reboiler. And we get reduced energy consumption by integrating the reboiler and the regenerator. And so we tested this at lab scale, where we measured the heat transfer to the rotating packed bed and also the solvent regeneration energy. And so we've developed correlations for heat transfer to the liquid inside the rotating packed bed. And we did that for water and for a solution that is representative of the most viscous amine solvents that we might encounter. And we also measured the regeneration energy for MEA. And we did 2 cases there, but one where we were preheating the solvent to 90 degrees centigrade, and the other where we were not preheating it at all. We were just feeding it at about 20 degrees centigrade. And the reason why the preheat cases have a high regeneration energy is because basically we ended up evaporating much more of the solvent or the water from the solvent than we needed to. But you can see here, the dashed line is what we'd expect the regeneration energy for MEA to be, and we're either on that line or just below it when we're using the integrated solvent, integrated stripper and reboiler. And basically, we've used that data to scale up, and this is the integrated stripper and reboiler being installed on the Higee core process in about April time this year. And that's all I've got to say. So on sort of technological innovations that we've come up with for CO2 capture, I'd just like to thank the researchers who work with me, and particularly James Hendry, who's involved in a lot of the scale-up work and the trials at 1 ton per day, and then also Obaidullah and Phil Chen, Abdullah Hai and Emily, who are working on different aspects of rotating packed bed. This work's been funded by the EU, by the UK Engineering and Physical Sciences Research Council, by the UK government, And we had support from Carbon Clean Solutions, from Mons, from Ultra Babcock, and Richard Allen Engineering, who build the rotating pat beds and who are involved in the HyRecall project, building that process. If you want to try out a solvent or test it in a rotating pat bed, in an intensified rotating pat bed plant, there's one being built at the Translational Energy Research Centre run by the University of Sheffield, and this is a picture of it. We recently used it for some trial work that we did with Procter & Gamble, but it's available for anyone who wants to use it. And thank you for listening. Have you got any questions?
Thank you very much, Jonathan. Very interesting talk. First question, do you know how much the cost is if you want to rent this unit? I can imagine that it's not cheap.
To rent at Turk?
Yeah, on this large unit that you just presented, how expensive is this? Because it seems huge.
Let's think. It's probably around about £10,000 a week.
Okay.
But based on the projects we've done there or are about to.
Yeah. Okay. Thank you. Quite some questions in our Q&A. So the first question is: I assume the optimum packing type to use is a compromise between efficiency and capacity, as with a conventional column. Can you comment on that?
Yes, it is. I mean, with a rotating pat bed, the capacity limit increases with the square of the speed. So even if you go to a packing that's more less porous and has higher surface area, you wouldn't have to increase the rotational speed all that much to get the same capacity for different types of packing. So the capacity issue is not quite as limiting as you might think if you go to a better packing. And it's, well, I mean, I'm just thinking early on, a lot of the sort of noise about rotating pat beds was of quite small rotating pat beds where the entrance zone was dominant. And so people have this idea that the performance is really super high all the way across the rotating pat bed, but it's not. And even I think you can use the variable porosity packings just to get your residence time up. I don't think they have a massive effect on the rate of mass transfer by changing to a higher surface area. But we've not looked in detail at that in terms of optimizing it.
Okay, thank you. So then, in the context of desorption using RPBs, have you looked at solvent degradation, both thermal and oxidative? Have you some experience in that?
We haven't, no. We haven't done long-term studies. The only long-term study was done, on the 1 ton per day demonstrator in Glasgow, but that was with Carbon Clean solvent, and that data is with Carbon Clean. But we haven't done any long-term studies with MEA.
Yeah. And then something in the material, issues with corrosion. Did you take any special stainless steel or something else that for the absorber or desorber?
Well, we build everything from 316 stainless steel, and so the packing and the rotors are made from 316 stainless steel.
316, yeah.
Yeah. I mean, the 1 ton per day unit, which ran on and off for about 3 years, there were never any corrosion issues with that unit. So.
Okay. And the last question is, could you please elaborate why the steam isn't directly contacted with the rotating pack bed?
Because we're trying to, I kind of understand where the confusion comes from, because generally when you've got a reboiler, on a solvent regeneration column, what comes off that reboiler is steam. There's a very little bit of amine in it, but it's mainly steam. But the point is to actually reduce that temperature difference between the solvent that's being heated and the steam. And when you reduce that temperature difference, then you're going to see some reductions in the amount of energy that you're using. So that's essentially the reason why we're heating the column externally and not directly injecting that steam. So it's part of the design to try and save energy for regeneration of the solvent. Yeah.
Thank you, Jonathan. Really impressive presentation, impressive work, and very nice to see this demonstrated at very high TRL already. With this, I would like to hand over the word to Georgios.
Yes, thank you very much, Kevin. Many thanks, Jonathan, for the very illustrative presentation. I'd also like to ask you something, if possible, before we move on to the next speaker. With this solution of integrating the reboiler and the rotating packed bed, I mean, what was the gain in the increase in energy efficiency? You mentioned that, but unless I missed it, I didn't see any numbers.
Yeah, well, I mean, the aim is to save about between 10 and 20% on the regeneration energy. So we have measured some data in the lab scale unit which shows some slight decrease in the energy consumption. But the aim is between 10 and 20%. I mean, the reason, I mean, it may not sound like much, but taken overall, it's not good enough just to shrink something. To say, we've got rotating packed bed and it shrunk the technology and it's cheaper to buy. Great, it's cheaper to buy, but the operating cost goes on for a long time. And so we were just really trying to offset the cost of the of rotating the packed beds in the first place.
Okay, many thanks. Very, very nice presentation. Very informative. With that, I'd like to move on to our third speaker, Michał Pawłowski, who's from Prospin, a rotating packed bed technology provider in Łódź, Poland. I'm sure that Michał is going to introduce the company and is going to talk about process and mechanical design correlation in RPP devices. Michał, the floor is yours.
Thank you for introduction. I would like to thank to Professor Stefanidis also to give me this opportunity to give you overview on my activity. I'm just trying to share my screen. Just a second. I think. Okay. I suppose. Good. Can you confirm? Can you see my screen now?
Yes. All good.
Thanks a lot. As Professor told, I represent here designer of RPB devices. To give you some correction, because in agenda there was some PhD degree mentioned. I don't have PhD degree, but it's a fact that I was working in academia at the beginning of my career at the mechanical and aeronautical faculty in Warsaw. So my background is mechanical engineering and mechanical design. After a short adventure with academia, I have switched my activity to design of chemical equipment apparatus for chemical industry, mainly for bulk materials drying. And that was something that inducted my meeting with Professor Andrzej Górak. He was chairman of Fluid Dynamics faculty in Technical University of Dortmund. And he was looking for somebody that will be able to design RPB for him. He bought some device which was already operable, and in that sense that it has some rotor and it was rotating. but it comes out that it was completely useless for him in his lab. Of course, the reason why is it's another lecture, another topic, but that was the first time I faced in this this kind of challenge when we have some guidelines from process chemical engineer what he wants to do, and we need to find mechanical solution answer, and we don't have good idea, good intermedia like book how to design RPB. There's now, even if we have some examples on market, some patents, it's not something that give us guidelines. So I have designed my first RPB looking at this device which he bought already, and what I shouldn't do, and I was trying to answer. That was the first time, since during the last 10 years, I provide 18 devices, and what I noticed, what you can notice here, I mark by the same color. I have marked the devices, that was designed with exactly the same design. It's just usually each device is slightly or much different, not only because of some mechanical improvement. Of course, we have some feedback if we design something, and then we'll see how it behaves in real conditions. But of course, there are some influence of mechanical solutions for chemical process, and we can improve it. But of course, there was some changes in size. But of course, it is very important to find proper solution for specific use, for specific process, for specific chemical system. Especially lab use is very demanding because it's quite universal, which is of course impossible to make all in one, but I'm trying to do it. And how to design RPB? This was the first question that I asked myself, and what it was already mentioned here. We can split it for two aspects, not independent, but at the beginning we can, let's say, we have example of the column. We need to lay it down here. Of course, we need to revert the dimensions. Height became the diameter became the height of the packing. The height became the length of the packing, but in fact, the length is not the radius. So it is quite easy to notice that we have some additional features here, like this space, this casing, and moreover, at least 1 degree of freedom, which is RPMs. So if we will get this dimensioning, what we should do here, we need to decide, for example, how to design the bearing system. If it has some influence on the process, obviously it is unexpectable. But if we want to design, for example, RPB for distillation process, and if we build the bearing system inside or near to rotor, which is obviously very it has very advantages in terms of mechanical design. We need to set the temperature for this operable temperature for this bearing. If we cool down it, somehow we can condensate the gas on the bearing system. If it will be too warm, it can evaporate our product if it's liquid product. So even this has some impact on the process. We can also ask the quite simple questions. Like if we want to make horizontal or vertical axis machine. For me, I prefer this design with vertical axis. But if we take a look at this aspect of additional feature like casing, we have the casing. We have some task that we want to realize in the casing. One is liquid drainage. And second thing is additional space, additional volume when we can react the gas and the liquid. So the behavior, here we have G, yes, the behavior of the liquid coming out of the rotor in this vertical design will be slightly different. In fact, we have mess here because with the liquid comes out, hit the walls, then falls down again to the rotor. It's not, maybe it can give us some advantages, but it is not easy to control it, not easy to model it. So this is one of the reasons. Of course, we can support it by bearing located here, which is not don't give us disadvantages that we have easy access to the internals. If we make support here, it will be quite easy to open the lid. But on the other hand, if we think about the very high packing, we cannot afford to do something like this because of bending moments of unbalance force and other problems. So at some dimensions that we came from here, we can think about different arrangement in even if that simple case, it might be horizontal or vertical axis. So in general, it has mutual influence with both that we can investigate and look for proper solution for specific field of use. This is our device that we have in our lab. And I would like to show just one thing related with the topic that I touched in other slide. What happened if the drops eject the rotor? It hit here and splashed to some fog, let's say. It depends on rotation speed, on the viscosity of the liquid, maybe on some surface tension, many parameters. So we can have different phenomena, casing phenomena, if we use different system and even different process parameter. What we can observe, for example, is to create the wave of liquid here on casing that is dragged by gas, by the rotor, and rotate with the rotor. It causes an extremely increase of power consumption and switch off the motor by overcurrent mistake. But anyway, we can use the stream breakers like this here. That gives us opportunity to drain the water liquid faster, but it's not always the advantages. Maybe at some process, at some parameters, we can increase the liquid holdup in the casing to use these advantages of perfect mixing inside the casing. We have quite perfect mixing, good mixing that we have checked, and it's really good mixing inside. So this is one of the different approach that we can have in different event processes. What is important also you can observe here is this is a very small device. It has just 100 to 250 millimeters of rotor diameter, and we use it for some proof of concepts of different process. Of course, if we look at the big scale process with great absolute amount of gas of liquid, like absorption, for example, of CO2, it's far away from even piloting scale. But we can make some screening of the solvents. We can make some tuning of the model. First point of some curves of the model that we built for calculating the packing and efficiency of the process. One important thing here is that here there's a packing height. Here there's the packing radius. So volume inside the casing is more than one order of magnitude higher than it will have in normal scale, because we would like to make it smaller. So the relation between packing volume and casing volume in absorption process, especially CO2 absorption, will be opposite. This is our lab setup with this small device. This is quite universal device which very additional features like heat exchanger inside the corpse, good range of acceleration and speed. We can use also 40 millimeters packing, 10 millimeters packing, so we can make double the efficiency of the liquid throughput, as for example, through this device. And below, I would like to show you some of results that we obtained related with absorption of CO2 with MEA. Because why? The point is that if we want to use RPB in CO2 capture, it's also worth to use RPB as the stripper. This is something that should work in closed loop, and this stripping RPB will be completely different device. Comes out that is completely different device than absorption RPB. What we can observe here with similar amount of flow rates, and when we make the flow double as the flow, we will still have the same efficiency of capture of stripping. Sorry. So this shows some untapping potential in this small device comparing the capture efficiency of CO2. Yes, the device for stripping will be much smaller, what we can observe from existing installation. And I would like to use this case to show this difference in approach if we design liquid drive process and gas life process. As I use just CO2 absorption as an example. And what if we calculate the RPB for the CO2 capture, the first point is we want to use low L2G ratio, liquid stream relation in mass, in weight, in kilograms between liquid and gas. Why? Because of liberty point. Yes, we want to make it efficient in terms of energy consumption. So the first limitation that we met will be here or here. I mean, the surface area and water entrainment. What we can observe also in upscaling, if we use small RPB, like in lab scale, the height of the packing is lower than half of the radius. This is that condition. So with half of the radius, we have the same speed of velocity of the gas entering the packing and the rotor eye. If we have quite high packing, the velocity, the limitation velocity will be here, and if we exceed 5 to 8 meters per second. It depends also on the liquid injection system, of course, but we can tune it to make it as high as possible, but just a few meters per second. That is something that limits us and give us the first dimension, inner radius of the rotor. Then we should calculate the size of the packing, the length of the packing. According to our model, this cross section is from 1/3 to square relation proportion, and our model is working in that sense that outcome is efficiency. We can put dimensions and solvent parameters, flow streams, and we will get efficiency of the outcome. Looking for optimal relation between dimensions is other task. It gives in terms of absorption, it was strictly related with packing volume. Of course, we want to have even packing wetting, so we shouldn't think about very high RPB to decrease the radius, but it's possible. For example, Baker Hughes installation has quite high RPB, cross-canal RPB. That's something like rotating column with what next? It's the solvent parameters and solvent. The parameters of the process. It's good to have atmospheric pressure because of the efficiency. in terms of energy consumption, because any compressor will have much higher consumption than RPB in this installation. And there are some topics related with upscaling that I will come back later. And if we look at the stripping device, we will have about 10% or 5% of gas flow, depends on concentration of CO2 in flow stream that we consider. We'll have quite liquid load and risk of flooding at this surface. So we can decrease this area, but we should prevent the flooding by proper RPMs and proper surface area inside. So when we look at the stripping of the MEA, the length of the packing is required. It's not so high. So we will get this opposite relation between in terms of absorption device, which give us also opportunity to put it horizontal. Just, for example, to have disadvantages that we can access, it will be lower, it will be not so high. We'll have good access for maintenance. Of course, additionally, we have temperature, pressure, or vacuum process difference in casing construction, sealing type, and many other points. We need to also think about heat exchange. What we already have is heat exchanger inside the corp, and we have some solution for also to build heat exchanger inside the rotor that we not realized till now, but still we are doing it for serious upscaling. So there's still some points how we should think about piloting if we want to make great upscale, how to increase packing volume in terms of packing type. In serious installation, we will have about 10 tons of packing. We need to keep it somehow inside the rotor. We use about 400 G acceleration here, so it is thousands of tons to keep somehow. We can use this material to keep itself, to be self-supporting if we use wind packing, but we need to choose it at the beginning. We need to tune our models. We need to think at the very beginning of our piloting. Also, very important thing is radius and power consumption. It's not so obvious that efficient radius in terms of capturing efficiency, capture rates will be efficient in terms of energy that we consume for capturing. And also we can think how to use casing effect. If the case is much smaller than volume of the packing, we can use it in the most efficient way. Maybe it's some optimal relation between radius and casing volume that allows us to use this device in more efficient way. So looking at this process, we have some conditions of the process. We have some dimensioning with the packing technical solution and some feedback that allows us to improve process condition or at least change the technical solution that we choose. Here on this picture, you can see in this row several of our device from early beginning, from the lowest volume to highest, and with one exception in this small device. And what I would like to show you here is this is pilot scale, even small pilot scale for CO2 capture. This small device can be used as full scale in purification of silicon oils from some organic pollution. So if we think about commercialization, it is much easier to build something like this and put it in some test rig to hire, to rent it, to prove it in real industry than bigger devices, especially for CO2 capture. This is what we are going to do next month. We are trying to build this kind of device and try in real process. And it's also opportunity if we found out that there are something under this question mark here. It's modular construction. We'll be able to change it, to adjust it, to improve device and adjust to the process that is not fully and well known, especially using RPB. This is also some opportunity how to convince production guy to use RPB instead of well-known technology. Maybe not the best, not efficient, but still well-known. So that was my idea. In this scale, RPB for CO2 capture looks like this. So it's huge. It requires some different approach to mechanical design. You can see here that we can reverse it upside down. Here is the motor. Opening the lid is rather useless with this tonnage. And we hang heavy rotor inside. The optimal range for this kind of device will be rather 300 RPM up to 200, depends on the radius, but for this radius I expect something like this. And it gives us a lot of question about the resonance speed of support, and that is also something that we need to answer in mechanical solution. The one important question here, which became most important for final user, is the power consumption, especially in CO2 capture. It's not so obvious how should we calculate. What is the optimal configuration? We know that there are some belt transmission RPB, like this old Belgian and other. We usually use direct drive, and we can, if we want to go with the RPM to lower, we can use multiple motor poles, but reasonable number in terms of availability on the market. I think finally we need to think about gear reducer, but still, what is the power consumption? It's not so obvious. We have quite well-known equation from TU Dortmund, and it's not so obvious how what is this factor. Of course, it's related with the unit, but this is idle power. But if we take a look at some model of the simple model of the energy consumption, which comes from velocity of drops that ejecting the rotor, we can calculate energy of each drop. We can after trivial transforms, we get this equation, which is exactly this, in fact. But this assumption, this is something that assumes that the velocity of the drops is equal to velocity of the rotor. It's not, obviously. It depends on viscosity, or maybe on surface tension, also on packing type, definitely. And if we would like to build this model and make some correction factor, we should put it somewhere in radius, which is in square. Because if we observe that we have some radial velocity and smaller velocity in this linear compound, it's definitely something that decreases the power consumption. I have made some tests. This curve shows the power calculation according to this TU Dortmund equation. This is this energy stream calculation, and this is real measurement that we have made on one of our device with this flow. Of course, if we use more viscous liquid, we'll place somewhere here. We are going to check sensitivity of this using glycerin with different viscosity, different density, and nearest weeks. I hope I will be able to have some idea and precise model, because the range, the discrepancy is huge. Most challenging use, in my opinion, is distillation RPB. The relation between dimension of the rotor is completely different than
if you can conclude in 2-3 minutes, that would be great.
Okay.
Please.
Just to finalize, this picture, quite well-known picture, as I suppose, comes from X-ray computer tomography of RPB, was made with a high liquid load, near flooding conditions. It's completely different, but here with distillation probably will have this kind of conditions. The most challenging thing is liquid distribution, influence of the liquid distribution on this pictures, on this liquid load inside the packing, and also the upper ceiling, which is predicted strictly for usually this ring is predicted strictly for working in one precise temperature. We are looking for good solutions still, and we are testing our devices and our solution. Thank you for your attention. There's a lot of course, I would like to just highlight some fields of investigation where we can look for some solutions, some stable guidelines, how to design, how to make something. We are participating. We are part of some colloquium, some conference where I would like to advertise when we meet academia and industrial partners, looking at the RPB development. And this year it will be organized by IFPEN Institute in France, in Lyon. Thank you very much.
Thanks a lot, Michał. Very interesting presentation, and you touched upon important matters that were also asked in the Q&A chat regarding, but we didn't have the time to discuss them, regarding challenges that are faced and rectified upon upscaling of RPBs or power consumption. You provided us with additional information. One thing I'd like to ask you is how you model these devices. Mechanical aspects are very important. There are essentially unlimited combinations of parameter values for different geometric aspects of your RPBs. How do you pick the optimal values, the optimal parameters? How do you model your systems?
Of course, it depends. The model that we use for absorption is based on the kinetics of the reaction and the equation of the kinetics. So we have quite a simple model. We don't use CFD to do it because, of course, it's great. It gives great pictures, but the final question from industry is what is the efficiency? What is the purity of some polypropylene? But the CFD model doesn't allow us to find a simple correlation between the drops and the effectivity. Finally, so we are trying to use some simple, well-known equation of kinetics of direction and some tuning factors that we can investigate in our lab or larger device from universities. Of course, we can find some limitation, like for example, droplets entrainment and so on. So this is also some limitation. We are trying to make some quite elastic design that allows us to adjust some parameters. Of course, that's other topic.
Okay. Regarding pressure, all the applications are atmospheric or subatmospheric pressure applications? No.
Okay. The higher pressurized RPB was predicted for 30 bars, which I designed. This RPB which we use in lab is predicted to work from full vacuum to about 5 bars. And usually the limitation criteria, this is stiffness of the corpus of the parts in small devices rather than pressure, so we can easily enlarge this pressure range up to 550, 60 bars.
Mm-hmm. And for what applications? This high pressure?
Now we have designed RPB with magnetic coupling up to 20 bars. It will be purification of silicon noise.
Okay.
It's not required exactly this kind of pressure, but we like to build universal device. So this is the opportunity that we'll have behind this solution.
Mm-hmm. And probably my last question is, there seems to be some discrepancy regarding the prediction of energy consumption by the TU Dortmund model and what you have measured, especially in the region of higher RPMs, right?
Yes, there's the big discrepancy. One thing is they have made it on RPB 600 with 10 millimeter slide of the packing. The question, which kind of packing? And 30% MEA. We have checked it with other solvents, with the water on RPB, which has 150 meters of the packing and 1 meter of the rotor diameter. What is the influence of the reaction between the plates if it's very narrow? There's a lot of question here. If we look at the small device, the criteria of choosing the motor power is rather speeding up and stopping the heavy rotor. But if we think about big scale RPB, we'll need to really precisely calculate the power consumption and also to reject this idle power related with some bearing, sealing, and system that does not have big impact on big packing and big devices.
Okay. Clear. Thank you very much. Very interesting, very informative presentation.
Thanks a lot. Thank you.
Thank you, Michał. And with that, I would like to move on to the fourth and final presentation of this webinar. We change gear now from RPBs to electrified turboreactor technology. This will be a presentation that will be delivered by Mike Bonheure. Mike works with Kevin on development of this novel technology, and they both promise that it will certainly reshape the chemical industry. I hope there's a sufficient argumentation and support of this bold argument. So, Mike, looking forward to your presentation. I think the entire audience does.
Cool. But indeed, it seems like I'm a bit, everybody sees my screen?
Yes.
Okay, great. Indeed seems that I'm a bit an outsider here because I'm absolutely not dealing with CO2. Instead, I'm really heading the completely other direction, and I'm talking about the electrification of chemical processes really from the get-go. So in the coming 25 minutes, I will basically introduce you to a completely new type of chemical reactor, which we refer to as a turboreactor. I will especially focus on their application in the steam cracking field, and we will also look at how and why this technology has specific benefits. Moreover, I will also walk you through some key sustainability challenges in conventional steam cracking and its electrified alternative. And finally, I of course need to introduce the Electro project, which is the initiative who brought everything together. But before I really can dive into turboreactors, it's important to level the playing field a bit and introduce you to the state of the art in steam cracking. So basically, steam cracking takes a highly saturated feedstock, anything ranging from ethane to butane, heavier naphtha feedstocks. And in the past decade, we also saw a clear shift towards more sustainable feedstocks, ranging from biomass to plastic waste. And we feed that feedstock basically in a massive furnace where we burn massive amounts of gas in order to reach temperatures of 700, 800, 900 degrees centigrade. Because under these high temperatures, the feedstock will start to decompose into smaller, economically more interesting components like ethylene, propylene, butadiene, basically components which we use in our everyday life. Just think about the tires of your car, the paint on the wall, and so on and so forth. Of course, with that massive demand, because it's used in everyday products, the amount of CO2 emissions is also massive. We are talking here about more than 250 million tons of CO2 equivalents each year. So that's why electrifying this process is such a game changer. By fully switching to electric heating, we are able to reduce the direct CO2 emissions by over 200 billion tons on an annual basis. Of course, we are not the first ones who realized this. As you can see from these snippets that I found online, there's been a clear surge in the past few years in R&D efforts, accelerating the development of e-crackers on an industrial scale. And of course, if you bring some of the brightest minds in the industry together to solve one single challenge, you know what will happen. Because during that same period that those companies started R&D agreements, we also see a clear surge in new intellectual property filings. Generally, we can categorize them into 4 main categories, ranging from resistive heating all the way down to microwave heating. But 2 of these clearly stand out in terms of activity in patent filings, and that is resistive heating and shockwave heating. Resistive heating, this is clearly where the big chemical players are coming in. They are filing multiple patents a year, and they are also developing multiple pilot plans as we speak. I think the most prominent example of that is the joint e-cracker project by BASF, Linde, and SABIC, who are currently running and testing a pilot at BASF Ludwigshafen. And then we have shockwave heating. It's not being backed as we speak by big chemical players, but it's backed by big turbomachinery players like Siemens Energy, but also backed by a small Finnish startup company named Coolbrook. And even though I have a lot to, I would like to talk about both technologies, I need to limit myself to only shockwave heating for the sake of time. Now, what are shockwaves? Well, the simplest way to think about shockwaves is by just imagining a highway full of cars, all cars driving at 120 kilometers an hour, and all of a sudden, one car makes a very abrupt move. What will happen? Well, a massive collision. It's a local disruption of the flow of the cars on the highway. And that's exactly also what is happening in supersonic flows. So basically, the flow at supersonic speed doesn't know what is happening in front of it. And all of a sudden, when particles need to move away because there is a sudden abrupt change in the geometry, a local disruption will take place, which we refer to as a shockwave. And a shockwave has very interesting properties because if you look at this very small, almost instant, it's very small, very local disruption, we also see that properties like pressure, temperature, density, and so on are changing almost instantaneously. When I'm talking about an instantaneous change, I'm really talking about change across several nanometers. And that's very interesting because we can leverage this type of heating in order to increase our temperature by a factor of 2, 3, 4, and even higher, depending on our incoming velocity. And this shockwave heating is exactly what is used in the rotodynamic reactor. It's a turboreactor designed, developed, and operated by Coolbrook. And indeed, these turboreactors are not merely theoretical in nature anymore because they are currently tested on pilot level, thereby processing multiple hundreds of kilograms per hour and successfully processing various hydrocarbon feedstocks, including naphtha, but also pyrolysis oils. But if you look at this image, what's really impressive is its size, because if you would position the rotodynamic reactor next to a steam cracker, as for example, displayed in this image, you would notice that the RDR is small. I would even refer to it as very tiny, because what we are looking at is a volume reduction of at least a factor 500 compared to conventional steam crackers. And this small footprint, of course, comes with massive advantages, because it's very compact. The time to build it on site is very small, reducing the overall capex of this new device. But let us have a closer look at the internals of this unit to truly capture and understand what is driving this compact design. So on your left, you basically see a cut view of the reactor, clearly showing that in a full 360 degrees rotodynamic reactor, we are basically having 2 toroidal halves. We have an upper reactor and a lower reactor. Each toroid is acting as a separate chemical reactor in order to really maximize the throughput of feedstock that can be processed per unit area. As you can notice on the right-hand figure, each toroid has its own inlet pipe, it also has its own outlet pipe. So they are really acting as independent reactors. The only thing they have in common is the shared impeller, which is rotating through both halves. Now, if we would track a single fluid parcel, what we would notice is that it enters the inlet, it enters the reactor through the inlet pipe, and that is then taken by the impeller in its corresponding toroidal reactor shape. This toroid has a very interesting benefit that it's basically allowing a lot of mixing to take place. But moreover, it also guides basically the flow from one side of the rotodynamic reactor to the other side of the rotodynamic reactor, where the process starts all over again. And so by passing multiple times in a regenerative manner through the impeller region, where the energy is added to our system, all the way down to the outlet pipe, where we will see very high temperatures. Now, how does this unit now really work? For that, we need to take a closer look to the bladed region. So the RDR comprises of three distinct bladed shapes: the nozzle, the impeller, which is rotating, and the diffuser. The nozzle is basically the blade which accelerates and distributes the fluid parcels over the impeller. The impeller will add kinetic energy onto our fluid and will accelerate it up to high subsonic level or even supersonic level. And in the diffuser, this kinetic energy is being diffused. We decelerate the flow in order to transform the kinetic energy into internal energy, allowing us to heat the flow from very cold flow to very hot flow. So you can imagine that by passing multiple times through this stage, the temperature will be increased every time, resulting in a 6-saw temperature profile. And by taking this 6-saw temperature profile and implement it in a low-dimensional reactor model, we can truly appreciate why the rotodynamic reactor is so much better compared to conventional steam cracking units, for example, the millisecond furnace. Because the first thing that you see is that the rate at which the rotodynamic reactor can heat up the flow is way higher. Moreover, its average operating temperature is also higher. And that shouldn't surprise, because the rotodynamic reactor heats the flow purely volumetric. So we don't have to deal with any type of heat transfer limitations as we witness in conventional steam cracking furnaces. On top of that, because we are operating at way higher temperatures compared to conventional steam crackers, our residence time can also be drastically reduced. And this comes with a quite nice benefit in steam cracking, because this has a direct impact on the light olefin yield. So here you basically see the light olefin yields compared between the turboreactor and the millisecond furnace. And what you can see is that both the ethylene and the propylene yields are higher compared to the millisecond furnace throughout the entire residence time of the rotodynamic reactor. How much higher, you might ask? Well, for this specific case, we estimate the increase to be 3.3 weight% absolute. So just to give you an idea, an increase of 0.1 weight% in light olefin yields amounts to approximately 1 million euros in pure profit. So an increase of 3.3 weight%, then we are talking about tens of millions of euros of pure profit by simply reinventing the way we transfer heat to the process fluid. Now, for the observing listeners, you might have noticed that besides the temperature that is increasing, also our pressure is increasing. And if there is one thing we don't really want to see in steam cracking, it's high pressures. And this is exactly what makes the RDR so unique, because the diffuser blades are designed with a very blunt trailing edge, thereby generating very intense turbulence, which leads to high levels of entropy generation. And it's really this turbulence, this entropy generation, which causes, instead of a pressure rise, a further increase in internal energy through the decay of turbulence into internal energy. So here, just downstream the diffuser, you really see a zone of high turbulent kinetic energy, a zone of high mixing, but it's still confined by the separation walls, which are implemented in the toroidal shape. But on top of that, you also see that the turbulent kinetic energy is breaking down very rapidly. And this with decay is very importantly to prevent mixing between the subsequent stages in our toroid, and also to provide a very uniform inflow heading towards the next stage. And here you basically can see what our CFD predictions are showing us. And what we see is a remarkable uniform static pressure distribution throughout the entire toroid. This uniformity is a direct result, of course, of the reactor's very open design, which minimizes pressure gradients along in the circumferential direction, but also ensures a very consistent flow dynamics and coherent flow structure generation within the reactor. Now, if we look at the temperature profile inside the rotodynamic reactor, we clearly can see well-defined regions. And these regions basically correspond to the different stages in the toroid. Because remember, every time the flow passes through our bladed region, energy is imparted onto our fluid, which will be transformed into internal energy and thus temperature. And so every time it passes, we see a clear increase in temperature, clearly being shown in the nicely delineated stages. But more remarkably is that we are able to increase the temperature by over 1,400 degrees centigrades in less than 50 milliseconds. It's that kind of rapid heating, which is simply impossible in conventional steam cracking furnaces. Now, in previous temperature profile that I've shown, that was a non-reactive case. So I basically assumed that the ethane which I fed in the system is not reacting, because by doing that, I was able to isolate and study the pure heating potential of the rotodynamic reactor. Of course, heating ethane to 1,400 degrees centigrade doesn't make much sense. So if we would enable real physics and enable the chemistry, we clearly can see a different temperature profile, but also there, that shouldn't be a big surprise. What we see is a big temperature drop, because of course, steam cracking, ethane cracking is highly endothermic. But what is also not very obvious are the different stages in temperature, but also there, that shouldn't be a big surprise, because of all energy that is imparted on our fluid, almost 60 to 70% is being consumed by the endothermicity of our chemical reactions. The remaining 40 to 30% is used for additional temperature increase. And as a result, our temperature jumps are less pronounced compared to a non-reactive case. Of course, when I say steam cracking, I also say coking. And what about coking? Well, based on our reactive CFD simulations, we were able to calculate the coking rates in the rotodynamic reactor using a well-known correlation from Reinier et al. And what we see is high coking rates. We see high coking rates there at the outlet pipe. On average, the coking rate in the outlet pipe is around 20 grams per hour per square meter. If you look at the peak coking rate, which is also located in the outlet pipe, we see that it amounts to around 35 grams per hour per square meter, which is along the same lines compared to conventional ethane crackers under the same operating conditions as what I've used for modeling the rotodynamic reactor. But there is one big advantage of the rotodynamic reactor is that we are using high-speed flow. And if I say high-speed flow, I'm also talking about enormous amounts of shear stress. So if we look at regions where we expect coking to occur, so really in regions with high temperatures, we also see that our shear stress is quite high. For example, on average, the shear stress in the outlet pipe is around 73 pascals. We even hit in different regions of the rotodynamic reactor, wall shear stresses easily exceeding 400 pascal. Under these conditions, coking will never be able to deposit on the reactor wall and will be simply swung away. Because if we compare it to conventional steam cracking tubes, for example, a straight bare tube or a swirl flow tube, we see that the wall shear stress there is around 6-7 pascals. So basically our wall shear stress is a factor 10 higher compared to conventional steam crackers. And so basically any coke that will be formed will be simply swept away out the reactor. Now that we have assessed the technicalities of the rotodynamic reactors, it's also very interesting to study its environmental impacts. And because the RDR is fully electrically driven, the carbon footprint of the electricity mix is, of course, a key factor in determining its environmental performance. And for that reason, we basically opted to analyze 4 different types of grids, ranging from the Norwegian grid, which has a high content of renewable energy, the Belgian grid, which has a high content of nuclear energy, the Dutch grid, which has a high content of fossil fuel-based energy, and then an average European grid, which has a high content of solid fuels like brown coal. And we compared those 4 cases to our base case. Our base case is a simple combustion-based state-of-the-art steam cracker. And it's from this figure, it becomes quite obvious that steam cracking, the electrification of steam cracking at least, is only meaningful in terms of CO2 reduction when the electricity that is being used is from a low carbon source. And that shouldn't surprise, because this is all attributed to the low efficiency of fossil fuel-based power plants, because a modern combined cycle power plant has a thermal efficiency of around 55–56%, while a conventional steam cracking furnace easily exceeds thermal efficiencies of 90%. So by connecting an electrified steam cracker onto a gray grid, we have an unavoidable destruction of exergy. This is further highlighted in this slide, where we once again see that depending on the electricity mix, the greenhouse gas prevention capabilities of electrified steam cracking is either good, for example, for the Norwegian grid, or is either detrimental. And then it's better to use for the base case steam crackers. Of course, when we would connect an electrified steam cracker like the rotodynamic reactor onto a full renewable grid like the Norwegian grid, the potential which it has to prevent the greenhouse gas emissions is the highest compared to other technology like the low emission or the hydrogen-based steam cracker units, with a reduction potential of around 27%. Also, based on this image, we were able to determine a cutoff point for e-crackers, and this would come down to 300 grams of CO2 equivalents per kilowatt hour. So if the electricity grid is below this number, it's sustainable, or it's more sustainable compared to the base case. If it is higher, it's less sustainable because of the carbon emissions coming from the energy source. But there is, of course, hope. Across Europe, the share of renewable electricity has been steadily rising across, in the past 2 decades. And in 2023, we clearly saw that renewables finally exceeded with quite a lot its production on the European grid. And with this, this trend is, of course, expected to continue. And as a result, the message becomes quite clear. E-cracking is no longer a futuristic concept. It's becoming a very viable and sustainable solution for the chemical industry. Of course, as you know, there is more to the story than just Scope 1 and Scope 2 emissions. In a conventional ethylene plants, most of Scope 1 emissions comes, of course, from furnaces, auxiliary boilers, and so on and so forth. And we can easily remove them through electrification. However, that's simply shifting basically our Scope 1 emissions to Scope 2 emissions. But also there, as highlighted in previous slides, our electricity grids become greener, and so by electrifying, we are also reducing our Scope 2 emissions as long as we can connect it to a sustainable electricity grid. But what is often overlooked is, of course, our Scope 3 emissions, because they can be as significant and in some cases even larger than Scope 1 and Scope 2 emissions. And this was clearly highlighted in a major industrial report. And I've taken the liberty, to be honest, to copy-paste a few key phrases, because the message is quite hard to ignore. Scope 3 emissions far outweigh Scope 1 and Scope 2 emissions. simply because the chemical industry still relies to this day on fossil fuel, on fossil-based feedstocks. So if we are really serious about decarbonizing this sector, tackling Scope 3 emissions is the biggest lever we currently have, but it's not a quick fix. It requires a full system-wide transformation across the entire value chain of the chemical industry. But this is also exactly where the RDR and other e-cracking technologies show a clear advantage, because the RDR delivers significantly higher light olefin yields compared to conventional technologies. It needs less feedstock to produce the same output, and less feedstock means lower Scope 3 emissions. And once again, this makes e-cracking not just an energy efficient option, but also a powerful approach for reducing upstream carbon footprint, which is where most of the emissions come from in the first place. Now, it's really in this light of Scope 3 emissions that I would like to introduce you to the Electro project. It's the European-funded initiative, which aims to create a true circular solution for the production of polyolefins. And at its core, this project basically combines two urgent goals in the chemical industry, which is on the one side, electrification, and on the other side, pure circularity, so circular feedstocks. Of course, if you want to address both in one single project, you need to surround yourself with a wide variety of experts. And that's also what we did. So here you basically see the map of our Electro Consortium partners, which includes 13 partners, both in Europe, but also outside Europe, ranging from large industrial players to research institutes, but also universities. And as you can see, we even included our campus in South Korea in order to give the project a broader international footprint and to really study the impact of plastics and plastic collection in a region outside Europe. Now, what do we really want to achieve within Electro? Well, within Electro, we basically defined 4 clear ambitions. The first thing what we want to do is valorize large volumes of unsorted plastic waste. We are targeting more than 50 kilotons per year using a robust 2-step extrusion method that gives us a high purity pyrolysis oils, even from highly contaminated or highly mixed waste, and make them suitable for electrified cracking. The second aspect is, of course, when you have that pyrolysis oils, you also want to make high-value olefin products from it. So think about the production of ethylene, think about the production of polypropylene or polyethylene, and so on. But instead of using fossil fuel naphtha, we are looking into utilizing the pyrolysis oil from scratch. And all of this we want to basically do in a full electrified system. So the entire process that we are currently designing in the Electro project should run on 100% renewable electricity. And finally, our aim with this entire goal is, of course, to reduce the greenhouse gas emissions by up to 90% across the entire life cycle of polyolefins. So within Electro, we are not just looking at a cleaner production, but we are really rethinking of how we make and recycle plastics. And that's really, we really start basically reinventing that entire process just from the ground up. And this brings me to some take-home messages. So I introduce you to the rotodynamic reactor. It's a novel turbomachine-based reactor, which can be used for the electrification of steam cracking, but also for the electrification of the general process industry. We've shown that the coking rates are at the same order of magnitude, even though it's operating at way higher coil outlet temperatures compared to conventional furnaces. And that electrification only makes sense if the unit which is being electrified is connected to an electricity grid with sufficiently renewable energy content onto it. Of course, as the renewable energy is steadily growing across Europe, it's quite clear that this will make the cut. And finally, I introduced basically the Electro project, which is not purely about cracking. It's really about reinventing the way we recycle, reuse, plastics and how to reinvent basically the entire polyolefin value chain. All of this work would, of course, not have been made possible without the people behind the Electro project, a team of dedicated researchers and partners who are really helping to turn this vision of a sustainable chemical industry into reality. That's the end of my talk. If you have any questions, it's my pleasure to answer them.
Yes, many thanks, Mike. It was a great talk on certainly a novel technology that has the potential to make the difference in the petrochemical industry. As I've mentioned a couple of times, because I'm a little bit aware of this technology, one of the really novel developments in the field of PI in the last years. That's my personal opinion. There was one question though in the Q&A field, which is a plausible one in my opinion. Do the shock waves, that's the question, erode the rotor and stator impellers? And how can you prevent that if that's the case?
So is the question, do the shock waves impact the blades?
Yeah.
Yeah, so the answer is yes. The shock waves are indeed impacting the diffuser blades, especially the diffuser blade, which causes additional mechanical stress onto those blades. But with proper engineering, and it's also not new because in that sense, supersonic turbo machines do exist in the industry, in aerospace. So it's certainly something we can come up with a solution for. But it's indeed impacting the blades.
Yeah. Okay. Then a more general one, well, it was also relevant for the other technologies. I remember at the beginning, coking was a concern. Then, as you presented, it turns out that with the CRH that are developed in this piece of equipment, then yeah, coke cannot get stuck on the walls and it will be swept away. Any other possible challenges that are expected to be faced upon upscaling?
Good question. I think there are many challenges still to be answered. Even though, well, a lot of the work that has been done as we speak is based on simulation work. Coolbrook is indeed currently testing the pilot. It's currently testing a pilot where some of the simulations are being validated. Some of the findings of the simulations are being validated. Now, I think the biggest issue that we might encounter is, are chemical companies willing to adopt this technology? Because it's completely new and they don't have any experience on how to operate this technology. Also, chemical companies have invested millions and billions in their traditional steam cracking plants. They are not very eager to simply replace them by a new technology. So I think if I need to mention one big hurdle that needs to be overcome for upscaling, I think it needs to be backed by big chemical players before we really can adopt it at big scale and really look into the upscaling of it.
Okay, clear. Although John Lee, who presented a little bit earlier, has probably identified one more challenge. And he asks whether the coke generated during cracking get deposited downstream from high shear zones of the reactor.
Yeah, so of course, coking is inherent to steam cracking, so we will form coke precursors, we will form cokes. So the good thing is the highest coking rates were predicted in the outlet pipe. So the outlet pipe is connected to the TLE. So yes, coke will form in the adiabatic region just in front of the TLE. So there the coke will deposit, that's for sure. Also in the reactor itself. So downstream of the diffuser, we also saw, especially close to the outlet, we saw high coking rate tendencies. So also there, cokes might be stuck. Well, some coke particles might travel up the toroid and will settle somewhere in the toroid itself. But most of the coking will just be swung out the reactor towards the TLE, where it will just settle.
All right. Probably you can inform the audience what is the status of development of the actual hardware. We'll give you the opportunity to validate these wonderful simulations.
Yes. So Coolbrook is currently operating their pilots, so they are testing a wide range of hydrocarbons right now, and they are expecting to really take the commercial step in 2025, 2026. So because now they are really partnering up with a lot of companies who are interested in this technology, be it for heating purposes or be it for real cracking purposes. So the first commercial launch on site is expected to be soon.
All right. Very good. I think we don't have any other questions, and in view of the time, we have to close the webinar. I'd like to thank you, Mike, and of course all the speakers for your talks. Great talks. We're a little bit behind schedule, but I think it was worth the effort and the time, because very important information was disseminated on technologies that essentially constitute the epitome of process intensification. So I don't know, Giorgio, whether you want to have a concluding remark.
No, I just want to thank all the speakers and attendees. We had a quite good participation throughout the presentation, and even if we are running late, we still have quite a large number of people attending. So this is the most effective way to demonstrate that all your presentations were quite interesting and well accepted by the audience. So many thanks and for organizing this event, to you, to Kevin, and to the speakers. And I wish you success in the implementation of such very interesting applications that would be very helpful for the future development of chemical engineering and industry. Okay. Thank you
Thanks a lot
on my side.
well. Bye-bye. Have a good afternoon, everyone.
Same to you. Okay, take care. Thanks again.
Bye-bye.
Ciao.
Bye.